In this video, let us learn to calculate the wavelength of the spectral lines of the mercury spectra by normal incident method using spectrometer and grating. First, let us get some basics of the spectrometer. We all know the least count of the spectrometer is 1 minute. Then we will learn how to take the readings or how to calculate the total readings from the vernier. If in case in the vernier the mind scale reading shows 60 degree and the vernier coincidence is 14, then the vernier scale reading is calculated as vernier coincidence into least count. So 14 into 1 minute is 14 minute. So the total reading is main scale reading plus vernier scale reading. So 60 degree plus 14 minutes will give you 60 degree 14 minutes. This is how we have to calculate the total readings for each and every reading of the vernier. Next, we need to know how to use the calculator for the calculation for the spectrometer experiments. We have to feed all the readings in terms of degrees and minutes to the calculator. So if you want to feed in the calculator, you could see a button there for feeding degrees and minutes. A finger pointer in the first picture may show you the degrees and the minutes. If you want to feed in 60 degree, press 6 followed by 0 and then press that button. So it becomes 60 degree. So that can be seen in the second picture. If you want to feed in minutes, in the third picture you see press 6 followed by 0 and then press degree, then press 1, feed 4, press 4 followed by the same button for the minutes. So the calculator will show 60 degree 14 minutes. For each and every degrees and minutes you have to press that button. Next, we need to find out the angle of diffraction. So in every table, over the top of the table, you have to write the least count equal to 1 minute and the direct ray reading as 0 degree and 180 degree or whatever you get it during the experiment as your direct ray reading. So in spectral lines, we have taken 1, 2, 3, 4, some 8 lines. And some professors may advise you to take the prominent colors or only 4 colors, or some may ask you to take the entire spectral lines like violet 1, violet 2, yellow 1, yellow 2, red 1, red 2, orange. So it varies from professor to professor. So okay, now we have the vernier 1, vernier 2 from the left direction and vernier 1, vernier 2 from the right direction. So from the left, for the vernier, the main scale reading is 210 degree and the vernier coincidence is 5. So the total reading is 210 degree 5 minutes. And for the vernier 2, the main scale reading is 30 degree and the vernier coincidence is 6. The total reading is 30 degree 6 minutes. So we should always see to that the difference between the vernier and vernier 2 is always 180 degree. The next set of reading you see the main scale reading is 209 degree 30 minutes and vernier coincidence is 10. So the total reading is 209 degree 40 minutes. For the vernier 2, the main scale reading is 29 degree 30 minutes and the vernier coincidence is 11. So the total reading has become 29 degree 41 minutes. In the same way, let us calculate the total reading for all the spectral lines for both the cases, for left as well as in the right direction. So in the next table, actually we used to put these two tables in a single page. For want of space, I have divided this table into 2 tables. See here, I have taken the vernier total readings of vernier 1, vernier 2 for the left and the total reading of vernier 1, vernier 2 to the right. For getting 2 theta, what we have to do is subtract the vernier 1 of the left and vernier 1 of the right. So I have highlighted in red color for the left and right vernier ones. So for the first reading, 238 degree 8 minutes minus 210 degree 5 minutes. The answer is 28 degree 3 minutes, which is highlighted in again in red color. So again the next, for the left vernier one, 209 degree 40 minutes, and for the right it is 238 degree 40 minutes. Subtract these two, you will get 29 degree. In the same way, for all the colors we have subtracted. For the red, you see, for the left vernier one it is 202 degree 50 minutes, and for the right vernier one it is 246 degree 46 minutes. If you subtract, you will get 43 degree 56 minutes for the left. In the same way, you subtract the vernier 2 readings of left and right, which is highlighted in blue color. See, for the first reading, the vernier 2 of the left is 30 degree 6 minutes and vernier 2 of the right is 58 degree 5 minutes. If you subtract, you will get 27 degree 59 minutes. For the last reading red, you see, for left vernier it is 22 degree 46 minutes, and for the right side the reading is 66 degree 42 minutes. If you subtract, you will get 43 degree 56 minutes. Now look at the 2 theta values of left and right. For the left it is 28 degree 3 minutes, and for the right it is 27 degree 59 minutes. Almost it's the same. Throughout from violet 1 to red, we could see the left and right readings of 2 theta are almost the same. So we can take the mean for this. If you take mean, that means for the violet one it is 28 degree 3 minutes plus 27 degree 59 minutes divided by 2 will give you 28 degree 1 minute. Next reading, 29 degree plus 28 degree 55 minutes divided by 2 will give you 28 degree 57 minutes. In the same way, let us calculate the mean of 2 theta till red. Then we have to calculate the angle of diffraction theta. Let us divide the 2 theta by 2. You will get 14 degree 28 minutes for violet 2. For blue it is 14 degree 57 minutes. So keep on dividing by 2. For the red we get 21 degree 58 minutes. So we have calculated the angle of diffraction. Next we need to find out the number of lines per meter in the grating. That means in a grating, in 1 meter of the grating, there are many lines drawn using a diamond pointer. So finding the number of lines per meter in the grating, or it is called as the standardization of the grating. So usually the grating is standardized with the spectral line green, because green is the mean of all colors. From our table we could see, for green the theta value is, that is the angle of diffraction, is 18 degree 26 minutes, and the lambda g, that is the wavelength of the green color, is 5461 angstrom, or 5461 into 10 power minus 10 meter, and m equal to 1 here, because we are using the first, we have taken the readings using the first order diffraction, so m is equal to 1. So throughout the calculation we will use m will be equal to 1, that is the order of diffraction. So to find the number of lines or number of rulings per meter in the grating, the formula is capital N is equal to sin theta m lambda g lines per meter. So the sine of theta value is 18 degree 26 minutes divided by m is 1, 5461 into 10 power minus 10 meter. So the sine of 18 degree 26 minutes is 0.3162 divided by 1 into 5461 into 10 power minus 10. So next divide the numerator and the denominator, you will get 5.7901 into 10 power minus 5. So in calculator itself you will get 5.7901 into 10 power minus 5, and the powers in the denominator, when they get into the numerator, you will get 10 power 10. The 10 power minus 10 in the denominator, when it goes to the numerator, it becomes 10 power 10. So 5.79 into 10 power minus 5 already is there, plus 10, so you will get 5.790 into 10 power 5 lines per meter. So the number of lines per meter in the grating is 5.790 into 10 power 5 lines per meter. And generally in a grating there will be 6 lakh lines in per meter in a grating. So we have got an answer almost closer to 6 into 10 power 5 lines per meter. So we have done the experiment correctly. So now we have found the number of lines per meter. Then let us find out the wavelength of the spectral lines of the mercury spectra. We all know the mercury spectra is white in color. When you send this mercury spectra through a grating, you will have different colors ranging from starting from violet to red. So first let us calculate the wavelength for the violet one. And the angle of diffraction for the violet one is the 14 degree, and m we know 1. N just now we have calculated, it is 5.790 into 10 power 5 lines per meter. So the formula lambda is equal to sine theta divided by mn meter. So we know the sine and the angle here is 14 degree. 1 divided by 1 into 5.790 into 10 power 5. Sine 14 degree is equal to 0.242 divided by 5.79 into 10 power 5. When you divide the numerator and the denominator, you will get 0.04178. And the 10 power plus 5 in the denominator, when it gets into the numerator, you will get, it becomes 10 power minus 5. Now I'm pulling the decimal power, or I want to make that decimal numbers into a whole number. So it becomes 4178 into 10 power. I have moved 5 decimal places. So it has become 4178 into 10 power minus 5. Already at 10 power minus 5 is there. So totally it is 4178 into 10 power minus 10 meters. So 10 power minus 10 meter is equal to 4178 angstrom. So the wavelength of the violet one is 4178 angstrom. So the theoretical value for the violet is 4046, I think. So we have got an almost a closer value for violet one. Next, let us calculate it for red. For the red, it is 21 degree 58 minutes and m equal to 1 as we know, and n is equal to 5.790 into 10 power 5 lines per meter. So putting all the values in the formula, sine of 21 degree 58 minutes divided by 1 into 5.79 into 10 power 5. Sine 21 degree 58 minutes is 0.3741 divided by 5.79 into 10 power 5. So dividing the numerator and the denominator, we get 0.06461 into 10 power minus 5. Again, moving 5 decimal points, we get 6461 into 10 power minus 5. Already another 10 power minus 5 is there. So this 10 power minus 5 and 10 power minus 5 will become 10 power minus 10. So we have got the lambda value as 6461 into 10 power minus 10 meters, or the wavelength of the red color of this mercury spectra is 6461 angstrom. And for the red color, it is around 6200 angstrom. So we have almost got a value which is closer to the theoretical value. So by the way, we can calculate the wavelength of the spectral lines of all the spectral lines. So and the results has been tabulated here. So for each spectral line, we have calculated the wavelength. So the calculated wavelength may vary around 200 to 300 angstrom with the theoretical value. Nothing wrong in it. So in this calculation, we have almost obtained all the wavelength closer to the theoretical value.